All right. So now we got to talk about some conceptual stuff here. So we've got all of the graphs that we've dealt with so far have been non-negative, which means that they're always above the x-axis. This is not always the case. So if you have a non-negative function, so your function is non-negative, and we integrate it under the curve, okay, the area then under the curve ends up being this positive value, this positive integral, which means integrate the area under the curve from, if your function, is negative, we integrate, we find the area under the curve. If those function values are negative, then the area ends up being considered negative. So this integral ends up, you got to be a little careful here. Area is never negative, but area can be assigned a direction. So in general, the integral from a to b of f of x does not give the area, but a net accumulation of the interval over time from a to b. So for instance, like from here, like let's say if I said find the integral from -5 to -2, and let's say this is 10. I don't know what it is. Let's just say that that area is 10 underneath the curve there. Well, if I said what's the integral from -5 to -2, you would say 10. But if I said what's the integral from -5 to 3, and let's say this was also 10. I know it's probably not, but let's just pretend that this is 10 because this is the below the x-axis. If I said the integral, maybe it's better if I write some of this down. Let's just pretend that this is 10. Let's pretend like this area also has an area of 10. So right now, if I said what's the integral from -5 to -2 of f of x dx, well, you'd say 10. If I said what's the integral from -2 to 3 of f of x dx, you would say -10. All right, now that area is 10, but the integral would be -10. And then if I could combine these, if I take the integral from -5 to 3 of f of x, then I'm going to end up having an overall integral value of 0 if those were 10s. Because this is a positive 10, all of these areas are positive above the x-axis, all these areas are under the x-axis, we consider those to be negative. All right, so hopefully that makes a little bit of sense. We're going to get some examples going here. Now, it depends on how you look at things, too. So let me go back here. I see if we're going to integrate from left to right, all right? So that means like what I did here. From left to right means I started at -5 and I went to -2. Then I went from -2 to 3. So when I integrate those, I just get those values. But when we go the other way, if you want to integrate from left to right, that all flips around. If you want to integrate from right to left, which you rarely want to do, but it ends up being the opposite of the actual value. Oh, I call it the actual value. I probably shouldn't call it. I should think of a better way to say that. But so this area under the curve, so if I went from -5 to -2, let's say that's 10 again. That area is 10. If I said, what's the integral from -5 to -2, you would say 10. If I said, what's the integral from -2 to -5, even though this is above the x-axis, because we went from this direction to this direction, we would consider that to be the negative. So if you notice, see how they said the integral from a to b is the opposite of the integral from b to a. So it always depends on how you look at it. If you ever need to flip an integral, this is what this is really doing for you. If you ever need to flip an integral, you just make it the opposite of what the integral was before. You can flip this around as long as you switch the sign. So look. Area is always positive. But we can sometimes consider that area, the integral can still be negative. So look at the way that he kind of broke this down here. This is the highlight that we're trying to get to. So the idea here is that if I want to figure out the integral from a to b, I can pick some spot in between from a to b, and I can calculate the area from a to c. So I'm going to pick something in between. Let me draw a little sketch over here. So here's a, here's b. Okay, and I've got some curve. I don't know whatever my curve is. Let's say my curve goes something like this. I don't know. I guess there, whatever. Okay, so if I wanted to integrate from a to b, I can choose to integrate from a to c. I can pick some spot in between them. I can take this integral, and then I can add it to this integral. So you can break up integrals, basically, is what that's saying. Now, why would we ever need that? Well, here's a perfect example. We're looking at a situation where you have a piecewise function. Your function changes. Your function changes at -1. It has a totally different look. So I'm going to pause you here and have you make a little sketch of what's going on. All right, let's see how you did. Ooh, no, I don't want to. I got -1 on this side. I'm going to draw it in the middle. I don't know, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And let's graph. Oh, the first one's pretty easy to sketch, huh? The function is 3 until we get to -1. Not included. So the area under the curve there is going to be really easy to figure out. And then the next part is going to be, what color can I use? How about a blue? So this is, we're going to start, this is basically slope-intercept form. So start at 2, down 1 over 1, down 1 over 1. Oh, what a nice coincidence. It fills in the gap there. All right, so what are we trying to actually figure out? So I've got a decent sketch going here. We want to figure out, write the integral expression that gives the area of the region bounded by the graph. So that's going to be some above and some below the x-axis. So I'm going to give you a pause here. I'm going to encourage you to pause here and try to write this up. Try to write an integral. Try to write something that looks like this for this story. All right, let's see how you did. I want to do the integral from -3 to 3. I'm just going to call the function f of x, then I don't have to write down all that junk. All right, now if you try to integrate this, I can't get one graph to fit. This thing doesn't just fit. Actually, let me highlight first. So we're going from -3 to 3, 1, 2, -3, to +3, 1, 2, 3. Oh, just that little bit's negative. Thanks a lot. So there isn't one shape that's above and so we got to break this up into two separate pieces: the piece of the function that's above the x-axis and the piece that's below the x-axis. So I'm going to let you try to rewrite this as two separate. Break this -3 to 3 thing up into two separate integrals. All right, let's see how you did. I'm going to start off with the integral. I want to go from -3, 1, 2, -0, 1, 2. I want to go from -3 to 2 first. That's going to find this area. Then I want to add on to that this little area here, which that means the integral from 2 until 3. So we can do this. You could do this algebraically if you wanted to actually plug them in there, or we can just do this graphically. I think it's probably just as quick to do graphically. So if I want to look at this shape, what kind of a shape are we talking about? You nailed it. This is a trapezoid. So my trapezoid formula would be 1/2 times my base. This is my base because these are the, this is my height. These are the bases because those are the parallel sides. My height would be the height of 3. Base 1 is a distance of 2. Base 2 is 1, 2, 3, 4, a distance of 5. Plus, all right, what shape is it? Try to figure out its area. So this is a little triangle. So that's going to be 1/2. Base is 1. And then the height, yeah, that's also 1. So we can start to clean this up, make this nice. Nope. So this is going to be, what's that? That's 7 times, that's 21 over 2. Plus, oh, this isn't so bad. So that's 22 over 2. So that's 11. Ah, never mind. Where'd I mess up? Let me go back. This is, sorry, let me try again with this triangle. This is a width, a base of 1. This is a height of -1. So that means that when I calculate this, this is 1/2 times 1 times -1. That's going to give me -1, which ends up being 20 over 2, or 10. All right, so we already talked a little bit about this using our calc. But so if I want to figure out the area of a region, that's a different question than the integral. So if I want to just find out the area of the region, you need to integrate this according to, you got to take the absolute value of those negative sections. We need to make sure that that area is added to the total. Let me show you a nice example here. So we're going to try to find e to the x minus 3. So what do you remember about the e to the x graph? See if you can sketch it. All right, so e to the x, I hope you remember e to the x is the one that whoosh, right, launches up like that. Now we've got a shift on, so my graph is shift down 3 spots. So I'm going to do a little, I don't know if you remember us doing this with the axes. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3. I wish I would have only drawn quadrant 1. But that is life. So I'm going to shift this origin down 1 to -3. And then the x-axis, the y-axis doesn't need a shift because our function's staying there. There's no shift next to x, so it doesn't push it left and right. So our exponential e to the anything is always 1. My bad. Let me try again. E to the 0 is 1. So when I plug in 0, I'm going to shift me up here. And then the e to the graph goes something like, I totally didn't look at my calculator just then. So my graph goes something like that. So unfortunately, we don't have a nice intercept here. All right, so let's kind of highlight what we're looking for. Use your calculator to find the area of the region. So that means I'm looking for area. That means I'm not integrating, because integration is accumulated change. So it would include the negative part and the positive part, and the negatives would cancel the positives. We're not talking about that. We're just finding the area. So we want of the graph, so that's the green part. The x-axis, that's the gray part. The vertical lines, x equals 0, that's basically the y-axis. And then I'm going to sketch another one over here. Let's do it in yellow at 3. So this is what I'm trying to figure out. I need to take this area. I'm going to call that capital A1. I'm going to take this area. I'm going to call that capital A2. And we're going to add those two areas together. Now, if you grab your calc and you type in, okay, here's my function, and then, so let's say you grab your calc. You type in your equation, e to the x minus 3. You graph it. And then you say, okay, second calc integrate from 0 to 3. All right, there we go. We get our answer of 10.8. No, this is wrong. This is wrong because this takes this area and it treats it as a negative. We want to find the area of the region bounded by this. That means I need to take both of those and add those areas together. I need those as separate areas. So it's tempting to integrate. It's tempting to do the integral from 0 to 3 of my function. Actually, I was looking at my notes, and I did this a couple years ago. This turns out to be 10.085. But this is wrong. This is incorrect because a sub 1 should be the absolute value of a sub 1. You know what I mean? Like we need to take this area here and make that area positive and add those two areas together. All right, so the good news is we still get to use our calculator. So I need to figure out where does my, I don't want to do this in integral. I do want to use a similar integral, but I want to break it up. I want to break it up when right there is where it transitions, when this function transitions from being a negative area to being a positive area, excuse me. So let's figure out where that location is. So I've already graphed my function. Now I need to figure out that, I hate it when it does that, so I'm going to change it. I just put 3 in there and makes it think that it's going to graph something new. All right, I need to know where this changes, that spot right there. What do we call that thing? Yeah, it's called a 0. So I can go into my calc. I can go find my zeros. We've done this a million times. Enter. Enter. Left bound, right bound, hit enter. Okay, so now this, from here, I'm going to save that. You can write this down if you want to. Actually, I guess I might as well write it down. This 0 occurs at 1.098. I don't like that I didn't write x equals in front of it. X equals 1.098. Now I'm going to use that though. I don't want to make an estimate if I don't have to, so I'm going to quit out of here and I'm going to store that now as alpha A. Ba-boom. All right, so from here, there's 2 ways you can do this. I'm going to start off by writing out my integral, and I'm going to call, so I don't have to keep writing out 1.0 blah, blah, blah. I'm going to say let capital A equal 1.098. All right, so what should our integral be? We're going to break it into 2 pieces. The first integral is going to go from 0 until this spot, which we called capital A. I really wish I wouldn't have called these A's, but hopefully that's not too confusing for you. Of my function, e to the x minus 3 dx, plus, then I want to, my bad, what did I forget to do? I want to make it the absolute value of that. You know what else I could have done is I could just throw a negative out in front of this too. That would have worked. Or I could have flipped those around and gone the other way. That would have worked too. Anyway, plus the integral from a until 3 of the absolute value of e to the x minus 3 dx. Lots of ways you could do this. You could graph this function and type all that stuff in. I'm going to just use my alpha f2 thing here. All right, so my first one goes from 0, alpha a, until, and remember, math, everything good on this screen is underneath math. Absolute, actually, no, I think that there's one, I'll show you on the next one. E to the x minus 3 dx. And you can hit enter here if you want to, or you can just keep going. I'm going to keep going. I'm going to integrate again. I'm going to go from a until 3. And then, like I said, alpha f2 also has the absolute value option there if you want to go that route of e to the x minus 3 dx. Totally different answer than what we had before. Remember the answer before when we just typed it into the calc was 10.085. Why is this number bigger? Hopefully you thought about it. It's because this was a negative, it took it away, and now we're adding that value on there. So our actual area is going to be equal to 12.677. Now, to be careful, if they put some units on there, you got to add some units, but luckily they don't have any units for us, so we don't have to worry about it. All right, so we can use definite integrals to help us find areas, but we can also use areas to help us find definite integrals. So yeah, that's the idea here, is that they're going to give us a hint of this area. They're going to give us a hint of this area. Right now, what's this area? Positive. What's this area? Also positive. When you integrate, that's what's going to cause that to be a negative, because it's an accumulation of these little rectangles that you could draw infinitely many little times in there and trying to squeeze up how tall they are or their area. Integrating from left to right, blah, blah, blah. Yeah, okay, so we got the idea. So what we're going to do is we want to take these and we want to rewrite them in terms of A1 and A2. All right, so if I go from -4 to -1, what's the integral? Well, it's the area of under the curve, and the area under the curve there is always positive, and it ends up always being the number A sub 1. All right, let's take a look at the next one. The integral from -1 to 4. -1 to 4. Now the area is A sub 2, but it's below the x-axis, so that would be negative A sub 2. Let's have you try a couple. Well, the first thing I notice here is that this is backwards, right? This goes from 4 into -1. Usually you want the smaller number on the bottom. That means you're allowed to just flip it around. This is the exact same as the opposite of -1 to 4 f of x dx. So we already know that the integral from -1 is this area. This area is negative because it's below the x-axis, but we're also taking the negative of that, so it actually turns it back into the positive A sub 2. All right, now I want to integrate from -4 to 4. We can't do that directly because some of our integral is above, some of our integral is below. So what we need to do instead is break it up into two separate integrals. I'm going to give you a chance to try to write up your integrals separately. All right, let's see how you did. So my first integral should go from -4 to -1 f of x dx, plus my second integral will go from -1 to +4 f of x dx. This integral is always all above, so that's A sub 1, plus this integral is always below, so that's negative A sub 2. So we would get A sub 1 minus A sub 2. Next up, well, that's easy. We just did that, right? So this integral we already know is A sub 1 minus A sub 2 minus 2 times, and we also already did this one 2 times. We did that right there, so that integral from negative is negative A sub 2. A sub 1 minus A sub 2 minus plus, so -1 A sub 2 plus 2, that ends up with, so we have A sub 1 minus 1 plus 2 is a positive